Hello, everyone, and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is advancements in primary current injection for low voltage circuit breaker testing. My name is Michael Fleischer, and I'm the digital marketing specialist for Megger. I'll be acting as a moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, a certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Jason Aaron, Applications Engineer. Also, to assist with the question and answer session, we will have joining us Volny Naranjo, Senior Applications Engineer, and Sanket Bolar, Applications Engineer. All right, let's go ahead and get started. Thank you so much for joining us today, Eric.
Thanks, Michael, and thanks everyone for joining us this afternoon. Today's presentation, as Michael said, will cover advancements in primary current injection for low voltage circuit breaker testing, and I'm Jason Aaron with the Technical Service Group out of Dallas, Texas. So our agenda today for our presentation, first we're going to jump into an introduction to primary injection testing, and then we're going to take a look at some fundamentals for low voltage circuit breakers, followed by reclosers and sectionalizer basics. Then we're going to take a look at some DC high-speed circuit breaker information, and then we're going to talk about the challenges for primary injection testing, and then finally take a look at some of the instruments that we're going to use while we're performing those tests. So now let's go ahead and dive into our primary injection section of our presentation. So what is primary current injection? Well, primary current injection is the only method that we can effectively use to do a functional test on circuit breakers and some other components. We'll talk about that here in a second. However, the thing is with primary current injection is it's the only method that we can use to verify that all the mechanisms within a circuit breaker are going to operate as intended whenever it's in use in a real world scenario. So, I mean, whenever we do this type of test, what we're going to do is we're going to drive current through a closed circuit breaker through the main contacts of the breaker and verify that the overcurrent function of the circuit breaker is going to react as intended, or trip whenever we push current through the breaker. Now, we talked about how primary injection applies to circuit breakers, but it also applies to reclosers, sectionalizers that have overcurrent function on those, DC high speed circuit breakers. But we can also use primary injection to do heat runs, test current transformers, verify the integrity of ground grids, and test personal protective grounds. Whenever we talk about primary current injection, there are always alternative methods that are mentioned for primary injection, but we have to understand what we're talking about when we talk about whenever we discuss those alternative methods. One that always comes up is secondary injection. And secondary injection is a means of testing a circuit breaker that has a solid state or an electronic trip unit. However, whenever we do that type of testing, that's the only part of the breaker that we're really testing. And you can see here that we have some different manufacturers' electronic trip units. And whenever we do a secondary injection test, you have a piece of equipment that'll connect to one of these electronic trip units and then check the functionality of it. However, there's a lot more going on with the circuit breaker whenever we test it than just the operation of that electronic element of the circuit breaker. One thing is, whenever we do primary current injection, is we're testing for the breaker's overall operation, as well as checking the logic of the trip unit to make sure that it's communicating properly with the other elements of the breaker, such as the current sensors and the wiring associated with the trip unit. In other words, whenever we do a primary current injection test, what we're really doing is we're doing a complete test on the system to verify that it's going to operate the way that we want it to whenever it needs to, so that we have reliable operation of the system. Another thing that we need to consider whenever we talk about primary current injection is the waveform that we're going to use whenever we do these primary current injection tests, because different different circuit breakers require different waveforms, but we also have different instruments that provide different outputs to be able to satisfy these requirements. One of the things that we see typically is for the AC waveform, where we have a typical multi-case circuit breaker similar to what we see here, where we have an AC current source to push current through the breaker and perform this primary current injection test. But another method that we see is using a DC waveform for certain types of circuit breakers, such as the one we see here, which is a high-speed DC circuit breaker that we would see used in railway infrastructure or DC vehicular applications. So now that we've talked about primary injection, let's talk about how that applies to low voltage circuit breakers. So what is it that we're talking about whenever we use the term circuit breaker? Well, we're talking about a device, an electrical device that can operate by a non-automatic means to open or close an electrical circuit, but also it can operate by an automatic means to to open a circuit at a predetermined overcurrent setting to protect that circuit. And something that's really important to understand is that whenever we talk about a circuit breaker, that circuit breaker needs to be able to withstand the amount of energy that could be produced by that fault condition. What are some characteristics that we want to understand whenever we talk about different circuit breakers? Well, a lot of the circuit breakers that we see whenever we do primary injection testing typically either have a metal frame, or they're an air insulated breaker, or a molded insulated case, where they use glass polyester or a thermoset composite resin to construct the case of the breaker. But also something that we need to consider whenever we talk about primary injection is whether or not, the design of the trip unit used whenever we talk about how the breaker is going to trip. Now, typically that can be either by electromechanical means or an electronic means. And whenever we talk about an electromechanical means, we talk about these two examples here. And the first one I'm going to talk about is a thermal element that has a bimetallic strip that will be in series with the circuit. And what will happen is whenever current is passed through the circuit, this bimetallic strip is going to heat up. And when it heats up, it's going to expand. And if it expands enough, then it's going to activate this trip bar to open the breaker. Additionally, it may have an element like this that's associated with the instantaneous trip function. And it operates similarly to what we just talked about, where the element is in line or in series with the current path. But what will happen is whenever there's enough current generated, this electromagnet is going to pull on this plunger and activate the trip bar and thus open the breaker. Excuse me. And whenever we talk about electronic trip units, here's an example of an electronic trip unit. And the way that these operate is there will be a set of current sensors that are mounted to the main conductors of the circuit breaker. And they'll communicate or send signals to this electronic trip unit to allow the breaker to trip. What will happen is this electronic trip unit will output to a trip mechanism and open the breaker. These are some different circuit breaker types that we see whenever we do primary injection testing. And this breaker here and this breaker here are examples of molded case circuit breakers. And as you can see, this this molded case circuit breaker is outfitted with an electronic trip unit. This breaker here and this one here are examples of the metal frame breakers that I was talking about earlier, and they're both outfitted with electronic trip units. And then this breaker here is an example of a miniature breaker that you may see in a control power scheme. So whenever we discuss circuit breakers, what's its purpose in a power distribution system? Well, we want it to be able to isolate a fault in your power distribution system whenever they occur. And the biggest reason that we want this is to limit any damage that it might do to the system whenever you have that fault condition occur. But also it's going to limit the outage area or sectionalize that part of the system so that you don't have more of your operation impacted by that fault. However, it's really important that we test and maintain this part of the system, because if it's unreliable, it can cause some pretty serious things such as injury to personnel, damage to property, or a more widespread outage area than what's desired. And in the end, all of these things lead to more expense. So what are some attributes that we want to see whenever we talk about a low voltage circuit breaker? Well, the first thing is that we need it to be a good conductor whenever the breaker is in the closed position. That way, whatever piece of equipment the breaker is supplying voltage to, that it's going to operate reliably and not have any kind of issues due to losses within the breaker. But also, we want the breaker, on the flip side of that, when we open it, we want it to be a good insulator to make sure that it properly isolates the circuit. Additionally, when we talk about breakers going from the close to the open position, it needs to transition quickly. What this is going to do is limit the amount of arcing that goes on within the breaker, so to prevent damage to the breaker itself. Also, that fast transition time is going to help us prevent power surges within the breaker and prevent transient overvoltage conditions that could happen through these switching processes. And last, it needs to be rigid and robust enough to withstand the fault energy that could be present due to a fault condition. So why do we test circuit breakers? Well, the easy answer to that is that circuit breakers fail, whether it be a mechanical malfunction such as broken parts or lack of lubrication, or say the current carrying parts fail due to heat, electrical stress, vibration, loose parts, or even a short circuit event. All of these things are going to contribute to failures within a circuit breaker. But if you can look at this graph that we have, this graph came from EPRI, and it's a representation of subcomponent failures when we talk about circuit breakers. And you can see that the vast majority of failures with circuit breakers has to do with the operating mechanism and the overcurrent trip element of the breaker. And we spoke earlier about alternatives to primary injection being a secondary injection test. Well, whenever we do that type of test, we're not testing those elements. The only way to really get a test that's going to evaluate these mechanisms and make sure that it's going to be reliable whenever you place it in service is a primary injection test. So whenever we talk about primary injection testing, it's very important that we understand how the time current curves apply to both pickup and the time delay values whenever we're doing this type of testing. Low voltage circuit breakers have different trip units, or excuse me, different trip functions that provide different protective elements based on the current level and the operating parameters of the system. Now, these functions are typically found as long time, short time, instantaneous, and ground faults. And we're going to dive a little bit more into what we're talking about whenever we refer to those functions. But first, let's talk about what they're protecting. So when we talk about long time and short time protective elements, we're usually talking about overload conditions that occur within a breaker. And these types of functions or trip scenarios are typically pretty low in current magnitude, but they generally happen, at least for a long time, over a long period of time. The short time function, however, is designed to trip a little bit faster, but this has to do with system coordination and selectability, and that's why this function exists in relation to overload condition. Also, other than the overload condition or the overload elements, we have instantaneous pickup, which is in reference to a short circuit condition. And you can see that the short circuit condition usually occurs at a very high current level. And typically this is the last thing that you want to see a breaker trip on, because it'll be the most violent and cause the most damage to an electrical system. So this is a physical representation of the mechanical hardware. Whenever we talk about relation to the overload element of a circuit breaker, we mentioned in the last slide that the overload conditions refer to your long time and your short time trip functions. Well, that's in relation to this physical mechanism within the breaker for the thermal protective functions. And we saw earlier that thermal protective function works off of a heating effect that occurs in the breaker whenever you have a certain amount of current that flows through the breaker. Additionally, this is the physical representation of the magnetic mechanism that we talked about earlier, that is in reference to the instantaneous function of the time current curve. So when we talk about the long time testing of a breaker, we're talking about the long time delay. And long time delay usually is set to trip over a period of time to simulate to protect an overload function, as we talked about in the last couple of slides. And typically, whenever we test this function, we're going to test it at a test current of 3 times, and then when we push current, we're going to time how long it takes to trip the breaker, and that trip time should fall within this band here that agrees with the time current curve that's published by the manufacturer of the equipment that we're testing. Now, for this example, we have to refer to the settings of the breaker before we begin to test. So for a long time, our long time setting is at 0.5 with a delay of 1. Now, the 0.5 refers to where the long time setting is going to pick up at, and we're going to test our long time, like I said, at 3 times. So this 0.5 value is in reference to the frame size of the breaker. So if we have 0.5 times 2000, that's 1000 amps. So if we're going to test at 3 times of the setting, then we're going to push 3000 amps continuously until the breaker trips. And the breaker should fall due to the fact that we have a delay band of 1, should fall within this time reference from the time current curve. If it falls outside of this time current curve, then we need to do some troubleshooting to evaluate what's going on with our breaker. So so for the short time test function, it's going to be similar to how we tested the long time test function, as in we're going to push continuous current and allow the current to continue to output until the breaker trips, and we're going to time how long that takes. However, we're going to do this a little bit differently in the way that we select the current level that we're going to use. Now, again, we have to refer to our trip unit settings to see where we're going to set our current at whenever we do this test. And for our short time, the short time setting is set at 2, but this 2 times pickup here is not in reference to the frame rating like long time is. It's in reference to the long time setting. So the long time setting, like we said before, was 1000 amps because it's 0.5 of 2000 or half of 2000. So 2 times 1000 amps is going to give 2 times 1000 amps is going to give us a test setting of 2000 amps. So to time our long time setting, we're going to test it at 1.5 times that. So our current level that we're going to use for that test is going to be 3000 amps. And so because our 3000 amps that we're using for the test is off of multiples of long time, and like we said, our long time setting is 1000, then this is where we're going to evaluate our trip current level at, and how we're going to evaluate the time that we need to validate those results. Now, our delay for short time is at 0.2 on curve, and this is the This is the trip current curve that we want to use for that on setting. Having a delay of 0.2 on, this is where our time is going to fall whenever we test the breaker and we evaluate the trip time. According to this curve, it should trip between 1.5 and 3 seconds. So our instantaneous tests, we're going to discuss that now, and it's a little bit different than the two tests that we just talked about, in that for an instantaneous test, this is a pickup test. It's going to be performed using a momentary current output. And the way that we do this test is we're going to start below our pickup point for the instantaneous setting, and then we're going to pulse current in increasing magnitudes until the breaker trips. And that's the pickup point, and we want to record the current value at which the breaker tripped. Typically, that current value is going to be plus or minus 10% of the pickup value for instantaneous for many electronic trip unit breakers. However, whenever you get into older style molded case breakers, that tolerance could be as much as plus or minus 25%. So a function that we haven't really talked about yet is the ground fault function. And ground fault function is tested similar to the long time and the short time function in that you're going to test it with a continuous current source. However, it's going to have its own set of pickup points, and you're going to have to refer to the manufacturer literature for the trip unit or breaker that you're testing to find out what that is. You can see here with this trip unit that it's not they don't give you a numerical value to represent what the settings are for ground fault. They're represented by letters. Well, to find out what these letters, what the current level is for each one of these alpha characters is to refer to the manufacturer's literature. And that way we know what the pickup level is for the ground fault setting and what to test at. Once we determine what that pickup value is, you're going to want to time that ground fault trip function at pushing 1.5 times whatever that pickup value is. And again, we're going to use that 1.5 multiple, and we're going to determine the time that we need to validate our results against. Another thing that's important to mention, though, whenever we talk about the ground fault test function is the fact that whenever we test the other functions of a circuit breaker, you're going to have to defeat or turn off the ground fault function on the breaker that you're testing, or any other function that you try to test, the ground fault function is going to take it out. And typically the way that we defeat this ground fault function is by one of two ways. The first way is for breakers that don't have an electronic trip unit or a set of secondary contacts, and that is to push current through series through two poles at one time in order to do this test. However, if you have a breaker that does have a set of secondary contacts, there's a possibility that you can jumper that out to defeat this function. But also, sometimes you have a secondary test set that may be provided for that trip unit that you can hook up and turn this function off. So we just mentioned a little previous snippet about auxiliary functions and how we can defeat ground fault sometimes by jumpering out those secondary contacts. Well, some things to consider whenever we are doing breaker testing is these functions or features and things that may be roadblocks whenever we're doing low voltage breaker testing. And the first one that I'd like to mention is a zone selective interlocking scheme, or ZSI. And ZSI is an interlocking system similar to the one seen here, where the breakers will communicate to each other for selective coordination of the way that they trip. And basically what happens with this is an upstream breaker will trip instantaneously on a fault if it's in the zone that it's being coordinated by. And it'll trip with the downstream breakers. You're probably asking yourself, well, why is this important to me? Well, if you have a breaker that has this feature and you don't defeat it, it can cause the breaker to trip prematurely and cause erroneous trip values whenever you're doing this primary injection testing. The next thing that we need to consider is the ground fault defeat that we just talked about in the last slide. And here is an example of a secondary injection test set that can be used on this style of breaker to defeat that ground fault function. Additionally, some things that we have to talk about or consider whenever we do this test are, is there presence of under voltage or over voltage mechanism that we have to satisfy using a external power source to be able to actually close the breaker to do these tests? Or is there a presence of a maintenance switch? What a maintenance switch will do is whenever you turn it on is it's going to default all your settings to the minimum values. And if for some reason it's on and you don't know it and you try to do a primary injection test, then obviously your breaker is going to trip prematurely and you're going to think that there's something wrong with it. So it's important to understand whether or not there is a maintenance switch on the breaker that you're testing. So now that we've discussed some things about low voltage circuit breakers and primary injection, let's move on and talk about reclosers and sectionalizers. So what is a recloser? Well, a recloser is an automatic high voltage electric switch, and it has an overcurrent sensing protection similar to a circuit breaker. However, whenever that overcurrent device operates and that recloser opens, it's going to attempt to close back in on the fault. And the reason it's doing this is in an attempt to clear transient faults that may be that may exist on the line. Now, it's not going to just continually open and close and open and close. It does have a maximum number of close attempts that it has. And once it does that, whether it be 2, 3, maybe 4 times for that recloser, then that recloser is going to lock out and not attempt to close again. It's going to consider that fault a permanent fault and it's going to lock out. These reclosers can be found in both single and 3-phase forms. We're going to talk a little bit more about that here in a minute and the applications of those different types of reclosers. For more information about the standards for testing reclosers or the specs that you want to see, refer to IEEE C37.60. So in complement to a recloser, sometimes there's a sectionalizer. And what a sectionalizer is it's a device that also has a protective device built into it. However, it's not built to function under a fault condition. It's built to open whenever there's a no load condition on the line. And what happens with this is after the recloser operates and it does its shot sequence and becomes locked out, what will happen is the sectionalizer will open to isolate the rest of the circuit. And if it's designed to do so, the recloser may reset and close back in. That's if there's other branches of the circuit involved with that power distribution system. So why do we need to use a recloser? Well, the easy answer is to increase reliability of a system. We spoke earlier about how a recloser will attempt to close back in to clear what we call transient faults. And those transient faults can be present during thunderstorms or other situations, such as wind-blown conductors may be pushed together and short them out, or maybe lightning or switching surges might cause problems where the voltage on the line may jump across the insulator or ground. Other situations are more environmental, such as birds, reptiles, or small animals may be on the line and shorted it out, or possibly even tree branches. All of these types of faults are considered temporary, and so whenever the recloser attempts to close back in, it may clear these faults and be able to close back in and maintain the operation of that power distribution system. Ultimately, what this does is it reduces the expense and the inconvenience caused by long-term power outages. So here are some different recloser types. We kind of mentioned earlier that we have single phase and 3-phase type of reclosers. Now, this first example here is of 3 single phase reclosers. And typically the application that we see for these is for a system that supplies a lot of single phase loads. And the reason that we want these reclosers to be able to operate independently is because if there is a permanent fault where one of the single phase reclosers becomes locked out, you still have the ability to maintain 2/3 of that load. Now, or 2/3 of the circuit that it's meant to power. Now, this one here is a 3-phase recloser, and the application typically for it is an application where you don't ever want the system to become to experience a single phase condition, such as a large motor or a transformer, that you just don't want it to see that single phase condition. Now, the last type that we'll talk about here is this is known as a single phase trip, 3-phase lockout. Excuse me, I'm sorry. This is a 3 single reclosers. And there's 3 different ways that this recloser can operate. The first is a single phase trip and a 3-phase lockout, where each phase is going to operate independently for both protective and closing functions. However, if it has one phase that moves to a lockout condition, then that it's deems as being a permanent fault, then all 3 phases are going to open and lock out. Also, it may have an operation where you have a 3-phase trip and a 3-phase lockout situation, where the overcurrent trip and the reclose sequences are all going to occur simultaneously, such as with the 3-phase system. So here's some control types for reclosers, and typically you're going to see either a hydraulic means of controlling the recloser or an electronic means of operating the recloser. Now, the hydraulic means is a majority of it is seen on single phase units, and these type of control units operate through a means of an overcurrent trip coil that is in series with the line that's going to the recloser. Now, during an overcurrent condition, the coil is going to control a plunger that's going to open the recloser contacts, and the timing and the sequencing events are going to occur by oil being pumped through separate hydraulic chambers within that recloser. The other style that we see, the electronic style recloser, is typically housed in a remote location where the cabinet is more accessible for easy access, and it's safer for the personnel working on the equipment. These type of controls are more flexible and offer more options than a traditional hydraulic unit, including automated functionality. These types of controls are often found for 3-phase reclosers. So now that we know what reclosers are, the purposes that they serve, some of the applications for them, and the way that they're controlled, you're probably wondering, well, how do I test these reclosers? Well, to test a recloser or a sectionalizer, we're going to want to push current through the device to evaluate its performance, similar to how we test a low voltage circuit breaker. However, the parameters that we're going to test whenever we test these devices is a little bit different. We're going to want to test the minimum pickup current point, or the point at which the device is going to trip. We're also going to want to test the performance of and do timing tests for the operation, the reclosing, and the total clearing time of the recloser. Now, what the total clearing time is when a recloser first experiences an overcurrent condition and it opens, it's going to try to close back in. However, there's a timer that starts the very first time that it trips, and if it closes back in and it maintains the circuit being closed, if it trips again and that timer is still active, in other words, that time hasn't, the total clearing time hasn't expired, then it's going to treat it as it's still the same cycle of events for the lockout purposes of the recloser. Something else that we're going to want to test whenever we do this is we're going to want to make sure and verify the number of operations to lock out for that recloser to make sure that it's operating the way that it's designed. And then we're going to want to make sure that the sequence of operations for the device also operate properly. The last thing that I want to mention whenever we do test these reclosers is that we want to do this a single shot to lockout test. And even though all of these processes can be kind of complicated or sound kind of complicated, the testing of these reclosers can be done safely and easily using a test set similar to the one we see here, which is an OCR, either the 15D model or the 50D model for higher current applications. And the test unit offers an automated user interface that helps make this testing more user-friendly for the technician. So now that we've talked about primary injection and low voltage circuit breakers, and we've touched on reclosers and sectionalizers, let's talk about how primary injection applies to DC high-speed circuit breakers. So what are DC high-speed circuit breakers? DC high-speed circuit breakers are a circuit breaker that are typically found in railway and DC vehicular applications. And per IEEE standard C37.14, a high-speed circuit breaker is one that limits the peak circuit current, the peak current during a fault condition. We're going to talk a little bit here in a minute about how that happens, but basically that operation needs to be quick enough to limit the development of that fault current that can happen whenever we have a fault condition. Now, these breakers are typically found in frame sizes between 1200 to 12,000 amps. They have a direct acting instantaneous trip element, and the standards that govern these breakers are IEC 61992-1 and -2, or IEEE standard C37.14 for DC breakers. So in our last slide, we talked about the fact that we want these high-speed DC circuit breakers to limit the amount of fault current that is produced whenever we have a fault. And how does that happen? Well, to understand how a high-speed circuit breaker limits fault current, we have to first understand what happens during an electrical fault. During an electrical fault or a short circuit condition, the current magnitude is going to increase very quickly. And we can see on our graph here that this is represented by a rise in the initial current and the rate of rise, which is represented by DI over DT or amps per second whenever this occurs. And the only way to really limit this this rate of rise is for the operating mechanism or the circuit breaker to operate very quickly. And so we want the current setting for the device to operate quick enough to help limit the growth of this current magnitude. And so we need to have it set low enough to respond, but we also need the device to operate very quickly to have a quick opening time. Therefore, we close off the current rise before it gets up here into the peak current that could develop. By doing so, limiting this opening time, as we saw down here, we have a current cutoff time that's still relatively low to how much current that could be sustained by this short circuit event. And we can see that our current cutoff time is down here as our prospective sustained short circuit current is a lot higher. And what we do by doing this is we limit the amount of short circuit current or the fault current that's developed whenever you have this occur, but also we limit the amount of arc fault energy that's created whenever this happens, because of the opening time, the amount of arc fault energy that was produced is very low, as we can see down here where our curve starts to increase. So we talk about the speed of these breakers limiting the amount of arc fault current that can be produced whenever we have a fault. Well, how fast do they open? Well, if you refer to this graph from Sectionalizer, which is a manufacturer of high-speed DC circuit breakers, and in relation to the rate of rise for current during a fault, this is how fast your current can rise at as much as 3 million amps per second, as far as the energy that's developed whenever you have this fault condition. And at a rate of rise in relation to this, the breakers are designed to trip within 4 to 5 milliseconds to be able to respond quick enough to limit that amount of fault energy that can be created from that overcurrent condition. And if you want to relate this to really how fast that 4 milliseconds is, well, it's less than 1/10 of a second, and that's how long it takes you to blink your eye. So this process of opening the breaker and clearing that fault happens faster than a blink of an eye. So how are these high-speed circuit breakers constructed? Well, they're similar to other types of circuit breakers where they have a frame, and that frame consists of 2 connection points for the current path. However, the connection point or the current carrying contacts are a little bit different in that they refer to it as a sliding contact. And you have the main pivot arm here, and it kind of slides back and forth inside the device. The direct release mechanism, or the IDS as it's often referred to, is the device that controls the trip function of the style of breakers. We're going to talk here in a minute how that operates and what it does whenever this mechanism functions. These style of breakers have a deionizing chamber or an arc chute similar to other low voltage breakers. The way that these breakers open and closes by electrical means, and that's done with this close coil referred to here. However, the closed coil doesn't have anything to do with the trip function of the device. And we're going to talk more about how that happens here in just a minute. And then lastly, you have some auxiliary contacts that are used for input and output purposes on the breaker. So we just looked at this direct release mechanism, and we talked about how it's the mechanism that helps to operate the overcurrent or the trip function for this style of breaker. And what happens with this mechanism is that it's an electromagnetic component, and the main current carrying component goes through the middle of this device. And what will happen is when it senses an overcurrent condition, this magnet here will move upwards and hit a fork, a mechanical fork that will force it open. And this happens, like we saw in the curve earlier, this happens very quickly. And it happens in a way that even though this closing coil is holding the breaker shut, it overrides that and forces it open. So how do we set the trip level on these high-speed DC circuit breakers? Well, we saw in the previous slide that the direct release device is used to trip a DC high-speed circuit breaker. But here we're going to see that the trip level is set using this screw mechanism on this device. And whenever we set this screw mechanism, what you're going to do is move this mechanism in and out to line up to whatever the divider is for the trip current level that we want to see. Now, this chart here is representative of a chart that you're going to find on the nameplate of a high-speed DC circuit breaker. And you can see how there's 2 different columns for current levels for that breaker, as well as an initial setting of the breaker that comes from the factory. These values here are representative of the values that you're going to find the breaker set at when it comes from the factory. All of these other settings are variable, but they depend on one factor, and that's whether or not this core mechanism within the IDS or the direct release mechanism is installed or not. If it's removed, then you're going to correlate with these lower values. However, if it's inserted, then you're going to correlate with these higher trip level values. Our example here is for this direct release device where the core is inserted. And you can see that the divider in relation to our 6,000 amps of trip current should be at 2.4. However, something that's important to notice is that the markers on this device are not identified in tenths of a divider. They're identified in whole numbers. So in order to set this, you have to have a general idea of where you want to set it, and then you have to have a quality DC current source to verify that the mechanism is set correctly. And this aspect of the setting of this mechanism, combined with the fact that you need these breakers to operate very quickly, so you need an immediate power dense current source to be able to do this test, is where the Megger Balto instrument comes in. We'll talk a little bit later in the presentation about what that is. So now let's talk about some challenges that we find whenever we do primary injection testing. So the first thing that we have to consider whenever we talk about the challenges of primary injection testing is the breaker's configuration. Now, is it a top fed or a bottom fed unit? What is the classification of the breaker? Is it a molded case breaker or a power circuit breaker? What are the different features that might influence the trip values and the way that we have to connect to the breaker whenever we do whenever we push current through the breaker? Additionally, we have to talk about or consider the features that we discussed earlier. One of the ones that we didn't mention earlier was thermal memory. And what thermal memory is when you repeatedly trip a circuit breaker, the breaker will heat up and it has that thermal function. And that thermal function has to be allowed to reset or cool down before you perform another function or another test on the breaker. What happens is if you try to repeatedly trip the breaker, it's just going to trip faster and faster. And the result of that is it's going to give you erroneous trip times whenever you try to test the breaker. Additionally, we've already talked about zone selective interlocking and how we may need to defeat that with different types of devices. Also, we talked about the possibility of an undervoltage coil and the fact that we may need a power source to defeat that, or the existence of a main switch. But the one thing that we really need to consider every time that we test a breaker is what is the trip unit type and how does it behave? Does it need external power to power up? Just because we push current through a breaker doesn't always mean that that breaker is going to trip, even if we push enough current, because sometimes that that trip unit needs an external power source or a secondary injection test set just to come on and operate. Another thing that we need to talk about whenever we discuss challenges for primary injection testing is where are we going to get the power source from for our test set, and what's the requirements for that test set? A lot of times, whenever we do this type of testing, you're pulling the power source from a generator or an inverter, but sometimes you're able to get it from a building circuit. However, you have to make sure that whatever source that you're using to power up that instrument is properly sized. You don't want to use a circuit breaker, or excuse me, a source that has a circuit breaker that's too small for the test set that you're going to use, because you're going to cause nuisance tripping of the circuit. I had an experience one time where I was testing in the field, and the customer was providing test voltage for my test set. They didn't adequately size not only the panel, but the breaker that was feeding the test set. Not only did the feeder breaker trip that was providing voltage to my test set, the main breaker in the panel tripped, and it took down their entire process. So that's why considering the needs of the test set and what you're doing whenever you do this type of testing is very important to understand. Another thing that's an aspect that influences your testing is test circuit impedance on this test circuit whenever you're testing. Now, many times this really isn't a problem because we're testing breakers that have stabs on the end of it, and you can stab it right onto the test set and you don't have that problem. However, sometimes you have to use cables going from your test set to the specimen that you're testing, similar to what we see here. Well, Something that can happen with this is the influence of impedance, and that can come about two different ways. One way is the length of the cables that you're using whenever you do this type of testing. You want to try to limit the length of those cables to negate the influence or this impedance influence due to that factor. But also something that can happen is the distance that you have between the two cables that are providing that voltage source, or excuse me, that current source to the specimen. If there's a lot of distance between those cables, it can create an inductive loop around, or a flux effect around that conductor. And what happens is that flux effect creates impedance on the cable. And what that impedance will do is not allow you to push as much current to the specimen as you think you are. So what you need to do is move the cables close together and wherever possible, excuse me, you need to twist these cables together to help provide that effect in both directions and neutralize that flux effect and negate that impedance influence on that circuit. Another thing that can occur whenever we're doing primary injection testing is the phenomenon of current decay. And what happens with this is whenever we do a continuous test on a circuit breaker, the element in that breaker can heat up. And as the element heats up and the cables heat up, as that current is flowing through them, there can be an impedance effect where the amount of current is going to decrease, and typically you would have to manually adjust that magnitude to keep it on track for the test. However, there is automatic means of getting over this hurdle, and that's by a continuous feedback loop. And the continuous feedback loop will continuously provide information to the breaker of how much current is being sent through the circuit to negate the influence of this current decay phenomenon. Also, something that we have to consider is a DC offset situation that can occur whenever we do an instantaneous trip on a breaker. And the presence of a DC offset in the current pulse can cause errors during an instantaneous test. And this DC offset will occur as a result of the reactance to resistance ratio of an inductive circuit. And the way that we can minimize this can either be by manual or automatic means. And this is done by adjusting the firing angle, or the point at which the voltage on the voltage wave that the output is energized. Now, the DC offset is going to be the difference between the peak and the RMS values whenever the test set starts the output current. And to prevent this, we can change the firing angle so that that peak and RMS value is close to the same to help create a symmetrical current source for testing. So now that we've discussed some of the challenges of primary injection testing, let's take a look at some of the instruments that we use whenever we do primary injection testing. The first one that we're going to take a look at is the Odin AT. And the Odin AT is a portable test set that can output up to 21,000 amps of test current. It's a very advanced unit and is extremely versatile. It has a central control unit, but then it also has up to 3 current units, and all of this can be tailored based to the needs that you have for whatever types of breakers or other equipment that you're testing and the amount of current that you need. Some of the other tests that this test instrument can do, you can test CTs with this instrument. You can also do polarity checks with it. You can do heat runs. You can also test automatic reclosers and sectionalizers with this piece of equipment, and you can also check the integrity of ground grids and safety grounds. But another unique feature that this instrument has is I over 30. And what that allows you to do is, if you have that feature selected before you start to do your tests, is it'll output a lower current than your test current to help you set the current that you need for your test. And what this does is it's going to allow you to avoid heating up that test element or that test device before you actually intend to do that test and record the values. Another instrument that we use for primary injection testing is the DDA, and the DDA comes in two different versions. We have the 3000 and the 6000, and the difference in the units is the amount of current that they can generate. The DDA 3000 will give you as much as 35,000 amps of test current, and the DDA 6000 will give you as much as 60,000 amps of high current output. These both units are operated by the DDA1, which is a digital interface used for breaker testing on the unit, but it also offers the ability to have variable pulse time and firing angle to be able to negate the influence of some of those challenges that we talked about whenever you do primary injection testing. Also, this test set is compliant with NEMA AB4 for breaker testing guidelines. Another instrument that we have for primary injection testing is the OCR 15D and the OCR 50D. And both of these test sets, as pictured here, operate in the same manner. The major difference, again, is just the amount of current that you can get from the instruments. And what both instruments are going to provide for you is they both operate, they have to have pre-programmed test sequences to help you do those performance tests on the reclosers like we talked about earlier, but also it has the ability to have impedance compensation to help overcome the influence of variable impedance that can happen with some reclosers. It has a digital user interface that's going to help for easy user operation, as well as it has a time current curve library that's going to help you test easier and more quickly instead of spending time having to research that information. And also it's compatible with PowerDB for easy record keeping. And last, we're going to talk about the Balto DC high current circuit breaker tester. Now, this test set here is excuse me, it's a test set that you're going to charge before you go out in the field. It operates by battery power and it's assisted by ultra capacitors. And what it's going to do is allow you to have that high current DC output for testing those DC high current circuit breakers. And it's going to give you that that power dense output very quickly to help test those high-speed circuit breakers within the amount of time that is required to validate those. This instrument is compliant with IEC 61992-2 for testing high-speed DC circuit breakers. It operates off of the Balto Win software for easy user interface and test report production. Okay, Michael, back to you.
Thanks, Jason. So at this time, the presentation portion of our webinar has officially concluded. We'll now take some time to answer as many of your questions as possible. If you have any questions, please submit them now to the Q&A box on the GoToWebinar control panel. For those of you that are leaving, when you close the webinar window, a survey should pop up on your screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon our future webinars. On the survey, there is a field for you to request a quote or a demo on any Megger products. Additionally, a copy of our presentation today, certificate of attendance, and a link to the video recording of this webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars, as well as register for upcoming webinars on our website at us.megger.com/webinars, and register for our next webinar on April 14th, titled You Ask, We Answer, a panel discussion on relay. All right, let's jump into your questions. Our first one I'm going to be directing over to Volny Naranjo. Volny, can you comment about the test leads? Is there a minimum and maximum length? What other aspects need to be considered?
Good, thank you, Michael. So, yeah, in one part of the presentation, we had a couple of slides talking about the length, and definitely the first thing is to minimize the length of the leads, as Jason indicated, to reduce the actual impedance. So remember, high current injection test sets, they basically provide high current by using a step-down transformer that takes whatever power supply you have and bring that to a very low voltage and increasing the current capability. So these low voltage at the output of the instrument can be easily defeated by an impedance that you connect there. So you always want to minimize the impedance. However, in if another thing to consider is that you should have a minimum length. Actually, I think it's NEMA 4AB that talks about at least 1 feet long of test leads. And we can verify these later on, but at the main concept is that let's think about a molded case circuit breaker. These breakers are counting with the bus bar or the cable connected to the terminals of the breaker to cool down, to refrigerate. It's kind of they use the cable as a dissipation means. So if you connect too short, the cable might not be able to dissipate the heat that is generated when testing. So that is important to consider as well. It's not always to go as the minimum length and just have a very short connection, and this will depend on, of course, on the breaker. And then the other aspect to consider is the twisting of the lead. So that's a very good or an important technique, a very simple technique to use to defeat the impedance that is created by the magnetic effect there, by the induction. So those, I guess, those are the aspects that we can elaborate on for this question.
Thank you, Wally. Our next question is going to go over to Sanket Bolar. Sanket, what other tests are performed on a circuit breaker?
So Jason focused on primary injection testing, and he also mentioned secondary injection testing. Besides that, some of the other tests that can be done include insulation resistance, where you check the insulation of the breaker. You can check the insulation between the poles. You can check the insulation between the poles and ground on the breaker. And the other test that you can do is a contact resistance measurement. You want to make sure that the contacts make a good connection, good solid connection, so that the current is conducted smoothly by the breaker without any heating issues, without any I²R losses. So to check the quality of the contacts, you can do a contact resistance measurement where a DC current is injected through the breaker, with the breaker in the closed condition, and the voltage drop is measured across each pole to find out what the resistance is. And this resistance is a small number, usually in the range of microohms, possibly milliohms in the case of really small breakers, but usually it's in microohms. This test can also be done during primary injection. So with AC current injection, you can also measure the voltage drop across each pole to find out what the contact resistance is.
Thank you, Sanket. Back over to Volney. Volney, does the instantaneous test measures the pickup current only, or does it also measure the operating time?
That's a good question, and I would say that it depends. So typically, in the common test is to test only or to determine the pickup. So instantaneous test will start like at 80% of the pickup value, and it will increase by pulsing the current and giving a little bit of a delay there for the breaker to cool down, and then it will increase the current in pulses. So the main purpose is to determine that pickup point well, if it is instantaneous, it is assumed that the breaker won't take too much to trip. However, some manufacturers provide the trip time, and in some ones is necessary to test that time that it takes to trip. So of course, if you're using one of these instruments, you're going to be able to determine that trip time. It's going to be matter of a couple of cycles, but you can measure it as well.
Thank you, Volney. Next over to Sanket. Sanket, why can't circuit breaker test sets be used to test reclosers?
Yeah, so when Jason was covering the products, he mentioned that the OCR 15D or 50D is what we use to test oil circuit reclosers. And the reason we have a separate test set for this particular application is because the way the primary injection test sets are built to test regular circuit breakers, they are capable of injecting thousands of amps, a huge amount of current, but the output voltage or the load voltage or the open circuit voltage is a very small number. It's usually just a few volts. In the case of reclosers have high impedance, which actually varies during the test, more so in the case of oil circuit reclosers, oil reclosers. So what happens is, because of the reclosers having a high amount of impedance, to be able to test those reclosers, you need a test system with a high amount of output voltage. And so the OCR 15D or 50D, this is a test set which has a high amount of voltage, which is capable of injecting whatever amperage is required through the recloser, and also capable of handling the changes, the changes in impedance of the recloser while the test is conducted, because the output voltage being high. That's why because of that requirement of the higher test voltage, we need a special instrument to be able to test oil reclosers.
All right, thanks, Sanket. So now our next question is going to be for Jason. Jason, can you give more detail how a sectionalizer operates and how it's controlled?
Yeah, sure. I can cover that. Let me bring this slide back up whenever I was talking about sectionalizers. So one thing that we talked about whenever we discussed sectionalizers is that they complement reclosers. And the reason they have to complement a recloser is because, as we talked about, there's no fault breaking capability for the sectionalizer. The sectionalizer, whenever it operates in an energized condition, it has to operate under basically a no load condition, or after the recloser has already operated and locked out. And this is just an example of how you would see that in a system. However, typically a system like this, you would have multiple sectionalizers for different branch circuits off of this one recloser. And what that would allow you to do is, after that recloser had opened, the sectionalizer could open for that one branch circuit off of the recloser. And after the time reset for the recloser, it could attempt to close back in, and that fault would no longer be present because the sectionalizer had opened and cleared that branch circuit off of that recloser. Your question was, can you give more details about the sectionalizer? And basically, that's the thing. It's a disconnect device, and it does have an overcurrent sensing element in it. However, it'll see the fault, but it won't open if there's a high current condition on the line, because it's not designed to open that way. It's designed to have the recloser isolate the circuit first, and then the sectionalizer will open to isolate a possible faulted connection from the recloser, so that when the recloser closes back in, it can sustain the load.
I have a kind of an additional comment to these. I would say that the sectionalizer, the recloser will have several branches connected to that recloser, or below that recloser there are several branches. So the purpose of the sectionalizer is to the sectionalizer is identifying the current, the high current. It's not operating, and it counts the operations in. Before the recloser close out, it will open that specific branch without locking out the recloser and leaving the rest of the branches that depend on that recloser out of service. So it's a way to kind of provide more reliability to the system and more service.
All right, thanks, guys. Our next question is back over to Jason. Jason, what applications are DC high-speed circuit breakers used in?
So DC high-speed circuit breakers are typically found in railway applications or traction power substations. They're also found in some DC applications or DC vehicular applications such as DC haul trucks. And the systems in the railway for the railway application have a rectifier system that supplies the system, and then the DC circuit breakers will operate to protect the system. And as we discussed earlier in the presentation about these DC high-speed circuit breakers, they're unique in the fact that their opening speed whenever there is a fault condition. However, they only have an instantaneous trip function. They don't operate in the same manner as the low voltage circuit breakers that we talked about that have the different type protected functions such as the long time and short time and additional ground fault protection of the circuit.
All right, thanks, Jason. Our next question is going to go over to Volney. Volney, in some breakers, it's necessary three-phase injection to check protections. How can I do that? Because I need current displacement in 120-degree angles.
Okay, so yeah, these are some specific applications, and I would say that there are very few three-phase current injection systems in the market, and if they are, they might not cover a big range of current. So an easy way or one solution that can be done is depending on the instrument that you have. You could have three of those instruments and connect them to three different phases. And then if the instrument has the ability to be controlled, to initiate the test from an external control, then you can connect them all together in parallel and initiate the test from the three different instruments at the same time. That's one solution that we have implemented, and it might be an expensive solution sometimes, but it's an option that it's there.
Thank you, Volney. While I have you, this next question is also for you. Where do you find how many cycles a breaker should trip in an instantaneous fault?
Okay, I guess this is a follow-up question from one of the previous questions and the answer I gave. So as I mentioned, this is very specific. Some manufacturers will do that, will provide that. So it will be in the manual of the circuit breaker, and again, it's going to be a very limited circuit breakers and manufacturers that have that.
All right, thanks a lot. So it looks like that's all the time we have for Q&A on this session. We apologize if we didn't get to your question today, but we will be working to follow up with you offline via email. As a reminder, a copy of this presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. I'd like to thank you all for attending. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. But once more, I'd like to thank you all for attending, and I hope you all have a great week.